All right, so for our next talk, we'll have Natalie Butterfield, who will be talking to you about radiation fundamentals and spectral lines. Take it away, Natalie.
Yes, as Brent said, my name is Natalie Butterfield. I'm an assistant scientist at NREO in Charlottesville, but I was a former postdoc here at GBO from 2018 to 2021, and so I'm pretty experienced with the GBT being a postdoc here. All right, so to start off my talk, I wanted to talk about the differences between continuum and spectral lines. So in the previous talk by Larry, we saw some background on continuum. And so the big difference between continuum and spectral lines is the frequency range. So continuum is broadband emission. So what we're seeing is emission that's over a wide range of frequencies. And if we compare that to spectral lines have narrowband emission. So it's kind of a line course that you can see here, which is covering a somewhat wider frequency range. But when you zoom in on any of these smaller sections of your frequency, you start to see these spectral lines, which are narrow band relative to some of the broader band continuum that we saw earlier. But it should be noted that many sources have a combination of both spectral lines and continuum emission. So here's kind of a nice plot by Eric Murphy, where it shows a bunch of different continuum sources. So they're all labeled up here. You can kind of see the combination of all of those emission mechanisms, along with two spectral lines that they've overplotted here. And the nice thing about showing this plot is that it's a good representation of the relative frequency ranges between continuum and spectral lines. The spectral lines are very, very narrow. They're basically like lines. They're these almost like delta-like functions relative to a broad band continuum. So I wanted to kind of stress the differences between continuum and spectral lines since we just saw continuum in the previous talk. Okay, so now let's move on to what are spectral lines. So spectral lines, all spectral lines have a rest frequency. So this is the frequency or wavelength at which a photon is emitted. So they have a known wavelength in your photon, and this is a signature for each photon that is emitted or for each spectral line. This value is known and can be derived, and I will be going into that a little bit later in my talk. So I just wanted to mention that here. And then all photons for the same line transition will have the same rest frequency. So this is not dependent on any of your source parameters. So for example, if you're looking at CO in the Milky Way galaxy, that line will have the same rest frequency as a line that was emitted in a high redshift galaxy. So these photons for the same line transition will have the same rest frequency. And this is not dependent on if you're looking at a gas cloud in the galaxy or some high redshift source. And one of the big things that I wanted to mention is that there's this Doppler shift of lines due to your source velocity. And so I have kind of the equation shown here, very simplistic, where essentially the velocity, the radial velocity of your source can be derived using the speed of light along with the change in wavelength. So that's basically how your wavelength here changes depending on your source velocity, and then the rest frequency or rest wavelength of your source. So now let's put this into perspective. What does this mean? So what this means is that for your sources that are moving, your observed wavelength that you're observing through your telescope is dependent on the velocity of your source there. All right, so this is an optical example, but I thought it was kind of a nice representation of what is actually going. This is a binary system where you have two stars and you're looking at the optical wavelength, but the same thing translates to radio wavelengths, where if you have a moving source, if it's moving basically perpendicular to your line of sight, you're not going to see that Doppler shift, but if it's moving towards you or if it's moving away from you, you would see that as blue shifted or red shifted respectively. So I wanted to also include the relativistic Doppler equation. So it's relativistic because it has this gamma factor up front. Now, if you're looking at something that's associated with the Milky Way galaxy or some source that has a very low velocity, source velocity, this ratio here essentially goes to 0, and so this essentially becomes unity. So you can ignore this term if you're looking at sources in the Milky Way, but if you're looking at high redshift galaxies, you might need to consider a gamma factor in there as well. So you need to know 2 of the 3 variables that are unknown here. So we know the speed of light, so it's the other 3 that you need to know 2 out of the 3 variables and just in order to solve for the third. So for example, if you know what the rest frequency is of your source and you know your source velocity, you can calculate what your observed frequency would be for your source, or vice versa. If you know your observed frequency, so let's say you detect a spectral line, you know what the rest frequency is of your line, you can calculate your source velocity. So any two combinations of those three, and you can solve for the third with this equation. And so that's how we can essentially calculate velocities or observed frequencies of our spectral lines. All right, so Larry had previously mentioned the radiative transfer, so I'm not going to go into the details since he went through all the equations for that, but I wanted to essentially outline what these different mechanisms are, put them into these diagrams here. And so we have three different types of main types of emission. We have spontaneous emission, we have the absorption, and then we have stimulated emission. So your spontaneous emission is where you have your you have a higher state, it essentially spontaneously decays into your lower state, and as it decays, it emits this photon here. Now, absorption is the opposite. You have a photon that comes into this lower state, you observe that or absorb that energy, and it boosts it to this higher state up here. And then lastly, the stimulated emission is where you have a upper state, you have a photon that comes by, it stimulates that emission to decay down and emit a photon as well. So you're actually getting two photons out of that as well. All right, so now what does this mean? How do we put this into perspective? So again, this is an optical example, but I thought it was kind of a nice way to tie all these things in together. So if you're looking at some, say, radio source, so this could be the sun, this could be some type of continuum emission. So you're looking at some type of radio continuum, you would see a continuous emission across your source. Now, if you're looking at some type of, for example, a gas cloud, something that has spectral lines, if you're looking at some background source as your light passes through, you would see that as absorption. Now, if you're looking at a source in itself, then you might see an emission spectrum that looks like this. So it all depends on what your orientation is relative to your sources, whether or not you maybe have a background source that's really bright, that's really hot, and then you might see an emission spectrum relative to that. But if you move slightly off of that source, so let's say you're looking at this direction, then you might instead see an emission spectrum. So your absorption is dependent on your line of sight between you, the absorbing source, and your background source. So I wanted to kind of put all that into perspective of what we mean by emission, absorption, and then the spontaneous type of decay. Okay, so to go through each one of these a little bit more detail. So spontaneous emission, that's where you just get a spontaneous decay from this upper state to the lower state and emitting a photon. So this is the most common type of emission that you get at these radio wavelengths, and it's tied to a lot of different spectral lines. So for example, CO, ammonia, H1, radio recombination lines, which I'll get into a little bit later in my talk, all of these will emit spontaneous decay. So this is where they spontaneously decay to this lower state and emit the photon. The next one, absorption. As I mentioned, you need to have some type of background continuum source in order to see this absorbing material. And there are several radio lines that are pretty common for absorption. I've listed just two of them up there. So for example, H1, I've seen a lot of studies that have detected absorption in H1, as well as formaldehyde. So those are two that are located at the radio wavelengths that are pretty common to observe in absorption. And so as I mentioned, you need to have your absorbing source in between you and the emitting source or your background continuum, so along your line of sight. And now I did want to mention this and stress this, since we will be seeing this later on in the lecture series, is that absorption is different than something that's known as negative bulls. So this is what Emily is going to talk about on Thursday, about feathering and why sometimes you need to feather single dish with interferometers. And so this is the image of an interferometry observation. And so you see these kind of negative features on either side of this bright continuum or a bright spectral line at the center. So I wanted to stress that this is different than the absorbing or absorption that I had mentioned earlier. These negative bulls are not real, it's just an imaging artifact. So I wanted to stress that, since I was mentioning absorption here, that they are different, but you'll see more of this in Emily's talk on Thursday. All right, so how do we observe spectral lines? So we observe spectral lines by taking what's known as a data cube. And so these data cubes are position, and then a frequency, velocity, wavelength as your third dimensional axis. So typically when you have a continuum image, you're just looking at this position versus position, you just get a basically 2D image. Whereas with a spectral line, you get this third dimension. And so that third dimension is your frequency or your velocity. And so you can see that here. So if you look at your top, that maybe is just a single channel or a single slice, or what you might see in continuum. And then as you're moving through and stepping through in your frequency or velocity, that's when you see specific spectral lines show up. And so this bright line that you see here is this kind of feature that they're showing in this diagram. And the same thing up here, you see these spectral lines in there, and that's associated with a single frequency or wavelength in your data cube. So your data cube is a position, and then that third axis is your velocity or your wavelength. And so that's how we study spectral lines, is by taking these data cubes. And so Will is going to talk about this more on Wednesday, but I did want to introduce this here since we are talking about spectral lines. So the GBT has a backend called Vegas. In Vegas, you can do different types of spectral setups depending on the type of science that you're doing, depending on the frequency that you're doing. And so there's a lot of different types of combinations that you can do in order to set up this data cube that we had seen earlier. So you can essentially identify what you want your channel widths to be, and what bandwidth, how wide you want this coverage to be in your data cube, how narrow you want these little steps to be in your data cube. And so all of those can be defined when you're doing this. So that's all I'm going to say on Vegas observing, since Will is going to talk about more about this on Wednesday, but I wanted to introduce that since I'm talking about spectral lines here. All right, so for the second half of my talk, I'm going to be talking about types of spectral line emission. All right, so the first one I'm going to cover is ionized gas. So I mentioned earlier in my talk about radio recombination lines. So radio recombination lines are essentially like the hydrogen alpha series that we see, like Balmer series or Lyman series, but it's just a higher end transition. So we're not looking at like the end 4 to or 5 to 4 or 4 to 3. We're looking at ones that are about 20 plus. Now 20 is kind of the upper end of ALMA, the radio telescope ALMA. Whereas if you're looking at, let's say around hand, you might be seeing transitions that have a in transition of about 100. So they do range widely, depending on what frequency range that you're at, but pretty much from like the upper end of a radio telescope, you see about 20. And then onwards down. And I think the highest number that they have in Splatolog, which we'll talk about in a minute, is about 500. So there's a wide range of different types of radio recombination lines, but essentially it's like the Balmer series or the Lyman series that we see in optical or UV. So essentially what you're getting is as the electron recombines with the proton, you're getting this cascade of the electron down to the ground state. So you get a transition of like the 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1. So it's cascading down as it recombines with the proton. And so each time it recombines or connects with that lower energy state, it emits a photon. And so what you can do is, because they trace the same type of emission regions, they trace the same type of sources, you can actually average multiple transitions together. So for example, the 64 and 63 alpha transitions, you can average those together in order to boost your signal to noise because they trace the same emission regions. Now, radio recombination lines are very faint. They're much fainter than any type of Bremsstrahlung emission, which is typically where you see this type of emission associated. Regions where you see Bremsstrahlung emission, you tend to see a lot of radio recon lines, but they're much, much fainter. So sometimes you need to use this technique in order to build up your signal to noise in order to get a detection or to do your science for your sources. And so because they're associated with this type of recombination, they're often observed near sites of star formation or towards H2 regions. All right, so you can calculate the recombination line frequency. So this is the frequency at which you observe these lines, your rest frequency. So there is a known equation where you take your two states. So essentially, if you have your, for example, your 110 state to your 109, and then your 110, your 109, which is shown here. And so you can calculate what your rest frequency would be for that transition state. So this is known as the 109 alpha transition, where it ends on the 109 state. And so That's how you can calculate it. But it's not just hydrogen atoms that have this recombination. The more common ones that you tend to see, hydrogen is definitely the most common and the brightest. However, you can also see helium recombination lines and carbon recombination lines. And so if you wanted to calculate those, there's also this equation down here, but you would just need to plug in for the carbon atoms or the helium atoms. And so just to kind of show that, what that would look like. So here we have the really bright hydrogen recombination line, but then you can also see that you have helium and then you have the carbon. So a lot of these, the way that you can set up your observations, you can target multiple recombination lines together in a single observation, or you can set up different spectral windows to target these individually if that's your science that you're interested in. But this is kind of a nice representation of the different intensity levels that you would expect to see. The hydrogen is definitely the brightest, followed by the helium, and then sometimes you can get the carbon if your source is bright enough. All right, so the next emission mechanism that I'm going to talk about is H1. So H1 is atomic hydrogen. So this is the 1420 gigahertz transition, or the 21 centimeter line. And this has to do with the spin flip of your electron in your hydrogen atom. So you have your higher energy state where you have your proton, you have your electron, and their spins are oriented in the same direction. And spontaneously, you'll get this flip down to this lower energy state where they're opposite direction. And that spin flip and the emitting photon has a frequency, rest frequency of 1420 megahertz. Now this type of emission is observed both through the interstellar medium and as well as the intergalactic medium. So if you're doing high redshift or extragalactic, H1 is kind of a common line to observe. And so here's kind of an example of a galaxy cluster or a galaxy group where you have your optical shown on this side, and then you have your radio H1 transitions shown on the other side. And so what you can see is that through optical, you kind of just see these, three galaxies. But when you look at it in H1, you can see that there's actually these tidal tails and this connection between the galaxies that's observed at radio that you really can't see when you observe it with optical. And so this can be the benefit of looking at some of these sources with radio wavelengths, is because there are certain features that you're not able to see at other wavelengths. All right, molecular gas. So the molecular gas that I'm going to be talking about for my slides today are the rotational radio transitions. And so what we mean by molecular gas is atom or 2+ atoms. So this is like CO or HCN or methanol, CH3OH. And so you need to have 2+ atoms in order to get a molecule. And so we're looking at molecules out in space. Now, typically at radio wavelengths, what we're looking at is we're looking at rotational spectra. So the example that I have up here is you have your 2 atoms. So let's say, for example, this is CO. And so what you're doing is you're getting this rotation about your axis. And that rotation we can observe at radio wavelengths. Typically, you can't have vibrational states. And so that's basically where the distance between your 2 atoms can vibrate or change. But that's more common to observe at infrared wavelengths. So for the purposes here, I'm going to be mainly talking about this rotational type of spectra. So in order to observe a rotational type spectra, you need to have a permanent dipole moment. So this means that you can't observe H2, which is the most common type of molecule to observe out in space, because these two masses of your 2 atoms on either side are the same. You need to have a permanent dipole moment in order to see this rotational emission spectrum. And so we can't actually observe an H2, but CO is thought to be a proxy of molecular hydrogen out in space. All right, so the slide that I have kind of down here, Slatalog, I wanted to introduce this as a nice repository of different types of spectral lines that you can observe. So it's not just molecular lines that are on here. I think H1 is also listed in Slatalog. There's also radio recombination lines, so pretty much any type of spectral lines. Slatalog is the one that I usually go to if I need to look up a rest frequency, or if I need to check any type of emission mechanisms. I usually go to Slatalog to find that. They've got a lot of nice quick boxes that you can use if you wanted to, for example, find HCN or HMC. any type of molecules, they have a listing here, or you can search for it. So I wanted to mention that as a nice tool if you are doing any type of molecular or spectroscopy. This is kind of a nice way to find some of those lines. Okay, so now I wanted to briefly discuss the different types of frequencies that you can get for your lines and how to calculate them, similar to what we looked at when we looked at the radio recon lines. So for example, the example that's given here is for the 1 to 0 CO molecule. And so we have our equation here to find our rest frequency of those lines. And so what you have is you have your J transitions here, the problems are constants, and then you need to calculate M and your RE. So what we have for our mass is just the mass of the carbon plus the mass of the oxygen, and you can calculate what that would be, and then you plug those in and you can find what your rest frequency is. Now, the one thing I wanted to stress on this slide here is that all of your future or higher J transitions are going to be a fundamental frequency of, or a frequency of the fundamental transition, which is your 1 to 0 transition. So, for example, the carbon monoxide 1 to 0 is at about 115 gigahertz. And then the second transition, which is located here, is about 230, and so forth and so forth. So they will all be harmonics of whatever that lower transition is, and that's how you can kind of, estimate where your lines will be. But if you wanted to calculate it, the equation is listed on the slide for your future reference as well. All right, so the last one, kind of moving back a little bit, is stimulated emission. And the reason why I put this slide a little bit later is because I wanted to talk about this in respect to masers, and a lot of these masers are associated with molecular lines. I wanted to include stimulated emission later on in my talk when I introduce these types of spectral lines. So now, as I had mentioned earlier, your stimulated emission is basically where you have a passing photon. That photon stimulates the upper transition state to decay down and also emit a photon as well. And so these photons will have the same frequency of their emission states. And so in order to get this type of amplified stimulated emission, you need to have really long path lengths. You need to have long path lengths so that as the photons are passing through, that they stimulate this emission as they're going, and that they build up enough signal, or they build up a bright signal, because you're getting this constant emission or stimulated emission as these photons are passing through. They tend to be point source-like with narrow line profiles, and I can show, this is kind of a VLA example, but it will show the point source-like nature of maser emission along with the bright or the very narrow line profile that you can get. And so this, what I'm showing here, is a class 1 maser emission. So this is methanol at class 1. So it's typically thought to be associated with collisional excitation. So that's like where you might have either outflows or maybe like cloud collisions or some type of internal collisions that are going on that stimulates the emission to emit at those higher at that maser type emission. There's also class 2 maser emission at methanol, and that's thought to be associated with radiation. So for example, these tend to be observed near high mass star forming regions where you might have a lot of UV rays that could be stimulating the emission that you need to get the maser type emission with these transitions here. There have been SiO and H2O masers as well. And then you can also get mega masers near AGN that have been observed as well. And so mega masers are thought to be where you have these really energetic masers that are thought to be observed near the nuclear region of distant galaxies. All right, so for the last part of my talk, I wanted to really focus on different types of science that you can do with spectral lines. So a lot of the topics that I'm going to be presenting here, so this isn't a full coverage of all the science that you can do with spectral lines. Science that you can do with spectral lines is constantly growing, but I wanted to kind of give an example of different types of science that you can do with spectral lines since we are covering this here. So the first one that I'm going to discuss is gas kinematics. So as we mentioned at the very start of my talk, that you can get this Doppler shift of lines. So based on your source velocity, you get the Doppler shift of lines, and that can tell you your velocity or your kinematics of your source. And so by looking at, there's several different types of techniques that you can do in order to investigate the kinematics of your source. And so I'll be covering these over the next few slides. So the first one, and probably the most simplistic, is to just take a spectra. So this is where you either put an aperture down, or maybe you're just taking a single position switching or frequency switching of your source, and you're just getting a spectra. And so spectra are basically you're extracting your intensity, so that's this axis, and you're plotting that intensity for each channel as a function of velocity or a function of frequency. And so essentially you see this type of, just spectral line emission. Now the pros of doing this type of analysis is that you can do velocity fitting. So that's what the blue curves are showing here, that you can fit basically the dynamics of your source. You can, with just Gaussians, or if you have a more complex molecule, for example, like ammonia, we have hyperfine fitting. There's a lot of different programs that have wrappers to account for those. But it's nice in the sense that you can do, if you have multiple components, which is what we had up here, that you are able to disentangle those. So for example, we have this sort of lower velocity wing in the source. And so when we fit it with just the two Gaussian components, so one here and one here, we saw this excess in the residuals, which suggests that there was a third component there. And so if you have multiple components or kind of a more complex region, doing this type of velocity fitting can help identify those different components and get their dispersion, get their intensities and parameters of those different lines. It's also helpful in identifying additional lines. So with the sensitivity of the GBT, there could be numerous additional lines in your spectrum, especially if you're looking at a spectral cloud, maybe that has a lot of different types of molecules. You can have dozens of additional lines in your spectrum. So what I'm showing here is basically it's a 3 millimeter observation where we had targeted several pretty prominent 3 millimeter lines. So for example, SIO, HDN. And when we were looking through our spectra, we noticed that several of these ones had additional lines in there. And so then we were able to use that Doppler shift equation that I had shown earlier in order to backtrack and find out what, identify what those lines are. So it can be helpful in identifying additional lines that you might have. And then looking for kinematic signatures. So absorption, a P-Signy profile, double form profiles. So sometimes you can get additional information by just looking at the spectra of your source. Now, the one con about doing spectral fitting or extracting the spectra is that you lose your spatial information. If you're averaging over your entire cloud, you lose that spatial information because you're summing up all of the emission that you have across your cloud, and so you lose that type of velocity flows or anything that could be positional or spatial information that's associated with that spectrum. But one of the other nice things that you can do, and here's kind of an example using each one, of looking at your spectrum, which is what they have here, and then being able to identify which spiral arms could be associated with those different spectra that you see, which is shown in this kind of example here. All right, so the next one that I'm going to talk about is moment maps. So now moment maps are, so it can differ depending on what type of moment you're using. And so I've listed a couple here. There's a bunch in the middle that I kind of skipped over, mainly just because of time reasons. But these 4 that we have here are the most common. So basically what you're doing is you're integrating your emission spectrum. So for example, the most simple one is moment 0. And so this is what your Gaussian or your line profile looks like, where your axis here is like your brightness temperature. And then you have like your velocity or frequency axis here. You're basically doing an integral and summing up all of the emission that's under your curve. That's all the moment 0 map is doing, is you're integrating over it. Now moment 1, which is known as a velocity field, is where you're doing it's the same, essentially the same thing. You're weighting it by your velocity in the top and then dividing it essentially by your moment 0 to find where that central velocity is, or what this line is here. Like where is this located in velocity space? Now your velocity dispersion, or moment 2, is essentially doing the same thing, shown by this equation here. But what you're trying to calculate here is your velocity dispersion, or how wide your graph is. And then the last one, moment 8, It depends on your source on whether or not you want to do this. All it's showing is it's basically looking through your data cube and saying what is the maximum pixel or maximum value for that pixel across your data cube. So you're essentially just grabbing this. Now, if you have really compact bright sources, so for example, masers, then you might want to do a maximum intensity map or a moment 8 to find where those masers are kind of located. So I didn't want to include that in here. It's not quite as common as the bottom 3 or top 3 that I have up here. But I did want to include it because there could be science cases of when you might want to do a maximum intensity map or a moment 8 map. Okay, so the pros and cons. So pros for doing moment maps that, especially for doing moment 1, is that you can see these large scale gas flows. So if you're looking at, let's say, for example, a rotation curve on a galaxy, you can see those as very clear velocity gradients for gas flows. Now the cons, it can be pretty poor at handling multiple components. So for example, the velocity dispersion, if you have multiple components in there, sometimes it can be, you can have confusion where it adds in those spectral lines. So say for example, you have a component here, then maybe a component here, and it's trying to fit across your wide range there. And so it can be pretty poor at handling multiple components. And then if you have really faint components, they can tend to be washed out. So these moment maps tend to work better for brighter, single components, but you can do certain tweaks where if you have kind of a velocity separation between your different components, or you can specify basically what you want your integral to be. So remember, this is an integral, so you can specify I want my integral to start from this velocity and go to this velocity, or if you have maybe a fainter component like what we had seen earlier, you can identify channels that are associated with that component as well. So you can identify what you want your limits to be on your integral when you're making these moment maps. And just to put this into context, so this was a paper that Amanda Kepley had, where she's showing the top row is showing HCN, this middle row is showing HCO plus, and then the bottom is showing those the moment 1 or the central velocity, where you can see this kind of velocity gradient or these curves here. And then on the top, she's kind of done a comparison with 3 gigahertz X-ray and then CO to do basically contours to show where the HCN moment 0, so that's that integrated emission, is located relative to some of these other multi-wavelength studies. And so this is kind of a nice way that you can do a comparison using moment maps. All right, and then the last one that I wanted to show relative to moment maps was the gas survey. So this was by Rachel Friesen, showing the Orion filament. And here you can see basically those first 3 that I had mentioned earlier, so moment 0, 1, and 2. The first one is essentially it's the contours that you're looking at here. It's not the background, it's the contours. And she's overlaying those contours on the hydrogen column density to show a relative distribution of where she's observing this ammonia emission relative to the continuum that you see here. And then your moment 1, which shows the velocity, you can see how you have really high velocities that are up in here, and then you kind of get some lower velocities down in this region there. And then your moment 2 is essentially showing you what your velocity dispersion or how wide your lines are. And for the most part, they seem to be relatively consistent, although in some places you might get a slightly higher velocity where maybe you have some type of feedback or something that could be producing those wider velocity dispersions that they see. So there's a lot of information that you can get from just doing moment maps with your lines. All right, channel maps. So channel maps is another way that you can investigate your data. And so this is essentially what you're doing is doing panel images at different velocities. So here, what we're looking at is, I think that's maybe around 180 or so kilometers per second and about 220. And so what we're doing is we're plotting each different channel that we have across our source, and you can see the different types of velocity flows and substructure across these different channels. So it's essentially a way of viewing your data cube, but plotting it as a 2D kind of image for a paper or something. So it's a nice way to visualize larger structures that you have. However, it's really only feasible over short velocity ranges. So if you're trying to observe this through like maybe a galaxy where you have hundreds of channels, it really becomes unfeasible at that moment. Now you can do something similar with channel maps, but for larger integrated channels. So you don't have to do the native resolution of your image. You could maybe bin it as 10 kilometer per second channels doing a moment 0, but and having different moment 0 maps where you've binned or integrated your emission over 10 kilometer per second channels in order to get it in a feasible type image like this. So there are different techniques that you can do if you have a really wide velocity range for your source. But for the most part, doing channel maps is really feasible if you have shorter kind of emission regions or velocity ranges. All right, position velocity diagram. So essentially what a position velocity diagram is, you make a slice across your source, and then what you're doing is for each one of these different points that you're making across your source, you're looking at what the spectral looks like. So you're plotting the position, which is kind of shown down here, your position versus velocity. And the example that I'm giving here is kind of a schematic that we did for one of the papers I did for my thesis, where we were looking at this expanding shell. And what we were arguing is that depending on where you did your position velocity slice, your emission would look different based on where that slice was taken across a uniformly expanding shell. So different phenomena have different signatures in position velocity slices, I'll show in the next example. And so by looking at what your position velocity slice looks like, you can get an understanding of the effects that are going on in your cloud or in your source. So the pros, it's a nice way to fit for your large scale velocity gradients. The cons, you are assuming that it's a large coherent structure in this case, in a single kind of extended source. So just to tie this back in, so this is an example of a high redshift galaxy, and you can kind of see the velocity gradients of the rotation curve. And so what they did was they did a position velocity slice in this direction, and this is what their position versus velocity looked like for this source here. And you can see this kind of signature of a galactic rotation there. All right, so the last one that I'm going to discuss for kinematics is about 3D visualization. And so this is where you can plot your data cube as a 3D figure. This has kind of been one of the growing ones that I've seen popping up over the last 5-10 years or so. So what you're doing is essentially you're looking at your data cube in 3D space. So you have your position, and then your velocity in this axis here. And what they did is that they're plotting for each one of their different components. They're plotting basically a data point for each one of those different positions in their data cube. So essentially what you're doing is it's a combination of both a position velocity diagram, you're looking at position velocity, and channel maps for each one of your different sources, because it's position, and velocity. Now the cons for doing this is that sometimes you can miss some phase emission that's in there. If there's any type of phase emission between these sources, it can be challenging to see that. Plus, it could be a little bit misleading when you're investigating correlated emission or large scale structures. Some of these features that might be similar in velocity space could be physically separated, for example, across the center of the galaxy, which is what they're showing here. This is an image of the CMZ. And so we have these multiple streams going on in the center of the galaxy. And so for certain regions, it could be misleading, where you might think that some of this emission is associated, where it could be versus the front and back of the galactic center. So just be aware that just because features look like they're located in close proximity in position velocity space does not necessarily mean that they are connected in physical space there. So just be aware of that if you ever plot these 3D type of visualizations. Okay, so for the last few minutes that I have, I wanted to talk about other cloud properties and other techniques. So for example, discussing dendrograms, gas temperature, dense gas fraction, gas mass, looking at different types of tracers. So for example, tracers are molecular lines that are associated with shocks versus star formation, or astrochemistry. And I'm not going to talk too much about astrochemistry because that's what Brett's going to be talking about tonight for his talk. So I wanted to mention it here as other types of science that you can do, but I'm not going to discuss that for my slides here. All right, so for the first one, dendrograms. So dendrograms, I would say within the last decade or so, dendrograms have been kind of this rising type of analysis. You can use them both with just position, and position, and velocity to find these structures. But essentially what you're doing is you're trying to determine the hierarchy of your cloud or identify sites of fragmentation where you have trunks, branches, and leaves. And so you can see that you have your kind of larger cloud here. You maybe have some clumps that are associated with your larger cloud. And then you have like compact structures within your cloud. And so what you're doing is you're identifying these substructures within your cloud by doing this hierarchy type of finding algorithm. So the nice thing about doing dendrograms is it's a systematic way of identifying these sources. So rather than going through and identifying them by eye, or saying, these are specific clouds or structures within your cloud, it allows you to reduce some bias in there, because you have to put in specific parameters to say this is what my floor is, to identify this larger structure, and then to have different types of signal levels on there, so it can help you reduce some bias in identifying these types of structures in there. It can be challenging with some bright emission or image artifacts, because you do have to pass through those parameters. So if you have some bright image artifacts, you could identify those as these structures in there. So you just want to make sure that you check when you have your final image what's identifying as these leaves and branches. But then you also can extract source properties, since it gives you out a region file. So you can say, okay, what is the spectra look like for this clump here? What is the gas mass that's associated with that clump there? So it's kind of a nice way to make your regions or identify your sources, which you can then go through and extract source properties for each one of those systematically. Gas temperature. So gas temperature, I'm showing this kind of plot here from Rachel Friesen's work. So essentially what you're doing when you're trying to do a gas temperature map or measurement is you're looking at your populations or your column density. So how much gas that you have in your different states versus your relative energy states for those different transitions, and using that information you can derive a gas temperature. So what that means is, say for example, you have a gas cloud that says it's maybe at 50 Kelvin or something. And so when you're measuring your two different energy states, you can say, okay, well, in order to get a certain population in those two states relative to each other, I need to have this type of temperature in order to populate those states. So that's essentially what you're doing when you're trying to find a gas temperature, is you're looking at two populations. So you do need to have two transitions of the same type of molecule in order to measure this type of gas temperature. But then you can get a lot of different information out of it. So the example that Rachel has here is from KFPA. So this is a GBT image looking at ammonia, and she's doing the populations of two states. So really what you can see here is it will tell you, you're looking at your temperatures across the top. So it will show you regions that are particularly warm, or potentially, some of the colder, kind of denser cloud cores, or potentially heating, maybe from feedback. So you can get a lot of information out of your structure to know what could be going on with your cloud to cause those different types of hot or cold cloud clumps. All right, so molecular tracers. So the first one I'm going to talk about, as I had mentioned, was shocks. So shocks can arise through a variety of different mechanisms. So you can have outflows. So say, for example, you have high mass star formation, they have these jets, or they have outflows that could be shocking the surrounding material. Maybe you have sliding clouds, or feedback maybe from outflows. There's a lot of different things that could be producing these shocks within these clouds. So the first one that I'm going to mention is SIO. This is a more common one to observe. I think the lowest transition is around 40 or so gigahertz, or you can observe it at 3 millimeters, around 90 gigahertz. But SIO is thought to be associated with strong shocks, and that's because of the way that the dust particles are set up. So a lot of times you get these silicate cores, and then you get some molecules that are kind of forming on the surface of these cores. And so when you get these cloud collisions or shocks that go through your propagating material, you're breaking apart that silicate core, which puts silicate in the gas phase, which can then connect with oxygen, forming SIO, similar to the way that you would observe CO with your types of electron states. Another one that's somewhat common to observe with shocks is HNCO. I think this is kind of a more recent one that I've seen, which is suggested to be observed with weak shocks. And then the last one, as I mentioned earlier, is the methanol class 1, which is thought to be collisionally pumped. So that's essentially where you have these shocks. Although I have seen some articles that argue instead of cosmic rays, so just be aware that there is a little bit of debate with that depending on the US. All right, star formation as a tracer. So the first one that I have listed up there was the methanol class 2. This is thought to be radiatively pumped, so found around star forming regions or high mass star forming regions where you get a lot of photons that are thought to pump these types of states. And so they're commonly found around active star forming regions. So for example, one of the massive star forming regions in the galactic center, SAGP2, is going to have these types of lasers. Radio recombination lines, I've added them here as tracers. They're not molecular lines, they're actually ionized gas, but they're found to be towards H2 regions. And the nice thing with doing radio recon lines is that it gives you the kinematic information of your ionized gas. And so that's kind of the plot that's shown here. It's the source in the galactic center, that is the circumnuclear disk around a supermassive black hole. But you can see that you can get a lot of different information by looking at these radio recon lines because it gives you the kinematic information. So you can see different types of velocity flows. So you can see this velocity gradient here. You can see regions where you might have multiple components. So for example, the sharp shift that you see from, is that about 0 or so kilometers per second down to about -200. That's probably a signature that what we're seeing is two different components along our line of sight because you're seeing that sharp shift. But it allows for a understanding of what the ionized gas is doing and how those flows could be related. And then you could always compare it with potentially a molecular emission that might be associated to identify, is this ionized gas maybe the ionized surface of a molecular cloud, by looking at this comparison between your ionized gas and maybe your molecular gas if you have that. All right, so I'm at 12 o'clock, so I'm at my 45 minutes, so I'm going to finish up with my summary. So we went over the difference between continuum and spectral lines, so that's really their frequency coverage. Spectral lines are very narrow, whereas continuum, you're going to see broadband emission. Each line has its own rest frequency, and then having the Doppler shift of those lines can give you your velocity information of your source. There's three main types of emission that we cover. So spontaneous, stimulated, and then absorption. And then there's lots of different types of emission that you can get. So ionized gas, H1, molecular gas, mesers. And then we briefly went over some of the science that we can do with spectral lines. Again, this is not all of the science. I only had a certain amount of time for this talk. So I kind of touched on some of the main topics here, but just be aware that there are a lot of other types of science that you can do with spectral lines. All right, and I will finish my talk there and take questions.
Great, thank you very much, Natalie. Lots of good science, and we have about 15 minutes for questions.
This might be a really basic question, but at one point you had mentioned mega masers. Is that just, how do you determine whether it's a mega maser or a regular maser? Is it just intensity?
Yeah, so it's intensity. I don't think there's any mega masers observed in the Milky Way. I think most of those are going to be extragalactic. And if you're looking at extragalactic, you're probably not going to be able to observe some of those like individual masers. And so most of the time, if you see a maser that's like in an extragalactic source, it's a mega maser. And if it's a galactic source, it tends to be just a normal maser. But the mechanisms, they're all the same for the masing emission. Okay. Yep.
When you said that you can combine transitions of lines, how do you do it? Do you just integrate for a longer time or to combine frequency?
Yeah, so most of the time when you combine transitions, I've usually seen that around radio recon lines when you average transitions. I think you can do it also with molecular transitions as well, but it's a little bit more hand wavy with those because you do get different types of J transitions there. Whereas with radio recombination lines, so this kind of topic here about combining them, what you're doing, what I've usually done is you need to make sure that your cubes are the same. So you need to make sure that your channel steps between them so that you're averaging, let's say, for example, 0 kilometers per second and then 1 kilometer per second and 2 kilometers per second, that those all line up between the two different transitions that you're using. So you don't want to have like the 0 kilometer per second in this cube averaging the 0.5 kilometer per second channel and this data. So you want to make sure that your cubes are identical, that they have the same step size, that they basically have the same type of imaging parameters, and then you can just add the two of them and divide by 2. It's just as simple as averaging them. Yep. And then your signal to noise will go down by a root of however many you average together. Yep. So that's typically how you do it. I mean, you could make your moment zero map and then average those, but sometimes it's nice to do it in this stage, especially if you want to do gas flows or some type of velocity information. It's better to do it at the higher stage rather than doing it at the end after you've made moment maps or spectra or anything like that.
Could I add a little bit there too?
Yeah.
Natalie? So for these two lines, those are very close together. The line profile should be pretty similar between those two, so you can probably just average them.
Yep.
If you're looking at recombination lines across 3 gigahertz or so, the line profile might change a little bit there. Your line will be broader at lower frequencies, narrower at the higher. So you might want to convolve.
Yeah, I would think something like that, like maybe you want to get your signal to noise higher, but as one of the lines is wider, you get it to get lower when you make the average. I don't know.
Yeah, you still win out by stacking them together. At least, I mean, this is mostly done in X band and C band, so between about 4 gigahertz and 12 gigahertz, and it's fine just to sort of make sure that your line profiles are the same and then average them together.
Any other questions?
This is kind of technical, but on your slide where you were fitting like the spectra for the gas kinematics, I just have like a general question. What program do you use to fit multiple Gaussians?
Yeah, so the spectra the program that I used to make both of these spectra was
Yeah.
PySpecket. The main push for using PySpecket in my graduate program was mainly because we had ammonia, and PySpecket has a ammonia wrapper in there to account for the hyperfine lines. So ammonia, you tend to see these types of like where your spectra looks something like this is your plot, you might get something that looks like this, and each one, all of these lines are associated with, for example, the NH311 transition or something. And so in order to account for those and having multiple components, you start to get a real blending between your different features. And so we use PySpecket in order to account for those because it had the underlying wrapper for it. But there's plotting Gaussians. I think there's like AstroPy programs and a lot of other programs that are out there, but that was the one that I used for this is PySpecket. Okay. Yep.
Got 2 questions online.
Okay.
First one, can we use the spectral line Doppler shift of radio waves to probe the plasma convection in the sun?
I don't do solar physics, so that was a good question. I don't know if anyone else here does solar physics to answer that question.
Presumably.
Yeah. Okay.
It depends on how narrow the line is and how
Yeah.
fast the convection current is, right? Okay, second question. How does the strong gravitational fields affect spectral lines at all? Strong gravitational fields affect spectral lines.
Presumably, yes. I mean, if you have let's say you're looking at a, accretion disk around there, if you're affecting the way that your photons, like redshifted or blue shifted photons, then presumably, yes. I have not looked at anything in that, like a really high strong magnetic field or.
So I believe that gravitational lensing has been confirmed by using spectral lines from the source.
Broaden.
Well, no, just like you see, like an Einstein ring, where you see the same source but multiple times. I believe spectral lines have been used. You observe each of those 4 sources in spectral lines, and they have the same spectral signatures. So I think they've been used to confirm, like, continuum suspected gravitational lensing. But I could do some. I can't point you at a reference, but I believe that's true.
Any other questions?
Chance, so any 2 molecules of element that emit this in the same frequency or close enough to appear the same frequency?
So, I mean, there are a lot of lines that have close frequencies. So in the first plot that I had shown where we had that line forest, I mean, you have a lot of lines that are, really close together on there. I don't know of any lines that have the exact same rest frequency. or close frequencies like that. But you could have potentially like, so if you have multiple components maybe along your line of sight, you could have them Doppler shifted to a similar frequency. But as for a rest frequency that have the identical or the same rest frequency, I don't know of any lines that have that, but there are many lines that are very, very close.
In recon lines, you can sometimes see like some alpha profiles overlapping with beta.
Yeah.
Like H beta
Mhm.
64 and H alpha 63 or something like that. And so that ruins both lines for you.
Okay.
Yeah. Any other- Anything else online?
Nothing else online? Carla?
Okay, if not, thank you very much, Natalie.